Okay, I hope everybody can hear me now. So we are talking about knowledge distillation, and we are talking about transferring the knowledge from the teacher model to the student model. And this is basically knowledge distillation is all about this. So when we are input an image to a teacher network, so the teacher provides us some probabilities for that image. And this task is basically the image classification task, if we are talking about basic terms. So we have, in this case, multiple classes, and we are talking about these two classes. So like this one is dog and this one is cat. So if it is giving us a probability that it's a cat, and it's like really sure, the teacher network is like really sure, okay, this is a cat, but we need to transfer this information to the student. But if we are going to transfer this transformation information directly to the student, then it becomes hard for the student to learn, because it is gonna okay memorize the type of image. Okay, this is the image, and I need to like target it as a cat instead of understanding why it is a cat. So we need to basically soften these probabilities. So this is one of the important things that we do in knowledge distillation, to soften the probability of output probabilities of the teacher network. So if we do something like this, that we after softening the probabilities, we will have probabilities like this, that is like not that extreme. And if we do it for like lots of examples, this would like be more it would be more comfortable for the students to learn, like okay, what kind of images I would classify into. So again, we will ask that, okay, why do we need to soften the larger probabilities? So there is a thing called dark knowledge, and it is basically hidden in the probability distributions of these larger models. So there are like subtle relationships when the big model is training. It starts from like these softened probabilities during training, and it as soon as it gets to train more and more on different data, it goes towards these extreme basically classifications. So these subtle relationships, like what is similar between cats and dogs and what is not, we need to transfer this knowledge from these big models to these smaller models. So in simpler terms, this knowledge distillation transfers this dark knowledge from the bigger models to the smaller ones without that much significant loss in performance. So how do we do that? So now we are gonna go towards the formal definition of knowledge distillation. So neural networks, for neural networks, we have this softmax function. So if we are talking about only classification loss, right? In this case, we have this softmax function we generally use for classification to generate the largest of class probabilities. So this is this softmax function. So basically, if we have like 5 classes and we output the probabilities, the class that has the highest probability would be predicted as the as the answer. So this is basically an exponential, and when we are talking about this IJ, this formula, so this is an exponential value, and the power of this exponent is basically e raised to power z I and divided by t. So ij are the number of classes here. So for any I like logit I, so zi is the current class, and we need to like okay divide all the probabilities of all the logit values of the other classes as well. So this is its formula. So the goal of the knowledge distillation is to align the class probabilities from like transfer this thing to distribution from teacher to the student network. So we are looking it in a probability distribution way. So as the teacher is the form of distribution the teacher is outputting for a specific image. So we have like 5 outputs for 5 different classes, and the teacher outputs a distribution, like and we need to like transfer this type of learning, this distribution towards the student as well, so that the student can mimic the larger model. And this T that you're seeing is basically the temperature term. And we basically use this temperature term to soften this probability. So this is an example. So if we have a cat image, we have this teacher network. Currently, if we do not use the T, or T, if T equals to 1, then the probability that we have from these networks is like really extreme. So, but we want to soften these probabilities. So we set t equals to, if it set t equals to 10, then these options that we have for different classes, this would be 59.9 and 40.1. So this is, so if anyone have any questions, they can raise their hands, and even like from the online people that are listening to me, we can like interactively answer questions so that everyone can follow along, right? If someone has confusion in this, I can like clear it, right? Okay. So yeah, this is the calculation that is shown here. So how it's we got these values. Okay. So we have this final loss we call the LKD, basically KD for knowledge distillation, which is a weighted sum of two parts balanced by a hyperparameter alpha. So as you can see, we have this L student and then we have L. So this is the complete loss. We have this L student. This L student is the like general loss that we use for any task. For classification loss, we generally use these binary, for two classes, we use binary cross entropy loss, and if it's a general, then categorical cross entropy loss. So this is for classification tasks. And this L distill, this is the class for knowledge distillation. We will also be looking at these losses. What kind of losses can we use for these tasks, right? And alpha, this alpha is basically providing weights to either what kind of weight do you need to put towards student loss as well as the distillation loss. So it's up to you, like what kind of, what do you need to like stress more on the knowledge distillation loss or the student loss. So it's up to you, yeah. So LKD is the final loss, L student is the cross entropy loss in the classification case, and L distillation loss, basically, it could be cross entropy loss, L2 loss, and as well as Kullback-Leibler divergence loss. So this is basically more direct towards the distribution, this Kullback-Leibler divergence. So it mimics the distribution between the teacher and the student outputs. And alpha is the weight, as we mentioned. So what to matching knowledge distillation? So what are the things that we actually match in these knowledge distillation tasks? So we have the different types of matching. So the simplest of it all is the output logits, as we discussed before in the previous example. So we have these output logits, then we have intermediate weights. Okay, what about the weights of the actual networks that we have two? So we have two networks, one is small, one is large. So we want, if we want like their weights to be closer, we have then intermediate features, gradients, sparsity patterns, and relational information, and we will go through one by one in the next slides. So matching output logits, if we are talking about matching logits, so it's the same thing that we discussed right now, and it is basically a comparison of the teacher and the student logit, and you can match it through like multiple ways, either cross entropy loss, L2 loss, as well as Kullback-Leibler loss, and that is the Kullback-Leibler divergence loss. That is the most used one. Then we have matching intermediate weights. So if we have like these two networks, teacher model and student model, right? We want to like match their weights that we have, the parameters, the values of the parameters that they have. So we want them to be similar so that they can output the same answers for different images and stuff. So this is also one way to do it. Then we have yeah, so this is an example of matching intermediate weights. So if we have this a teacher's network and this is a student network, so you can say that this one is a smaller one and this one is a big one. And so we want to like, okay, match these weights, but how do we, you can see that there is a difference between the, like their shapes of the weights here, like they have like different depth or their width is different in this case. So how do we match them? So we use an intermediate convolution, this fully connected layer, so that so this weights can be converted to this level, the same size as this one, and then we can like see how much different are they between the output of this layer as well as this weight. So that's how we mesh them. So other than cross entropy distillation loss, also we can also add L2 loss between the teacher weights and the students went. So basically this linear transformation allows us to like convert these smaller weights to the bigger shape, and then we can like, okay, compare them with the loss and make them like more closer to each other in a semantic way. Okay, so the third thing that we can match is the intermediate features. So there is a difference between intermediate weights and intermediate features. Weights are the actual parameter values in the model, but intermediate features basically are the outputs of those basically layer or the output layers in this case. And these outputs, so we want, or in other words, you can say that the activation maps that we have. So you can match these activation maps or intermediate features also. So the intuition behind is that if we are talking about activation maps from different layers between these teacher and students, so they should also match throughout the network. So if they are matching, then we can say that, okay, their outputs will also be matched in this case. So if we are minimizing the maximum mean discrepancy between these intermediate features, then we can also have a student model that is acting like more closer to the teacher one, and we'll have good outputs in this case. Then we have an intermediate attention map. So this attention feature basically is the idea, okay, basically at which place in an image the model is focusing more on. So basically, gradients of feature maps are used to characterize attention in deep neural networks, right? So we do it using these gradient values, and these gradient values in different feature maps, when we set the intermediate feature maps, these tell us like, okay, where the model is focusing on. So the attention of a CNN feature map is defined as basically this is the X, this is the input, and L is basically the loss, where L is the learning objective. So yeah, so basically if in any case, if we have these intermediate features, if we change the intermediate features of our model at any place in the model, with respect to the loss, then what kind of perturbations we achieve there, or what kind of changes we would get. So that gives us information, okay, which are the sensitive parts of our intermediate feature maps in the model. That gives us like an idea. So so then this follows that, okay, so the attention maps of these two models, the teacher model and student model, should also match. So from there we get this idea, and we do this also like using these first calculating these attention maps, and based on that we calculate the reduce them, like we calculate their how much they are close to each other. So if we are talking about these if you are inputting one, and we have this ResNet 34 and ResNet 105, these are two models with, so this has 101 layers and this has 34 layers. So you can say that, okay, these have different types of, activation maps, but their performance, like these are like closer because this is a lot closer to, since activation maps are closer, the performance is closer compared to a model that is that does not have similar attention maps in this case. Yeah. So any questions until now, or if I'm going too fast, then please stop me and I'll go a little bit slower, right? Okay, I think no questions here. So yeah, so we talked about integer meter maps. So this is integer intermediate attention map. So this is sort of the same thing. We use losses between those attention maps, and then we try to do that. And then we have these matching these sparsity patterns. So by matching these sparsity patterns, we mean that, okay, when we are like using a convolutional neural network and we pass different feature maps through ReLU activation functions. So whenever we pass a feature map through a ReLU activation function, so that it gives us either a positive value or a zero value, right? So based on that, we will have to, we can see that, okay, if the sparsity patterns of these feature maps within the neural network on different stages, if they are matching, then it means the two neural networks are also acting in the same way. So this is also an idea we can use for matching their like matching their performance sort of. So yeah. So you can see that within these two neural networks, we are talking about intermediate sparsity patterns. Where are the zeros located? What kind of maps do we have in this case, right? And the sixth type that we have is relations between different layers. So by that, what we mean is that, okay, if we have these layer modules, this is a block, and this block has like, okay, 5 layers. So we have a convolution layer, then batch normalization ReLU, then we have convolution layer, and then batch normalization. So this consists of overall uh, five layers that has different operations in this case. And at the end, we also have another ReLU. So what we do is that we take the input of this block as well as the output of this block, and then we do take their inner product. So we have a matrix of shape C in and C out. So input channels cross output channels. We have this, a 2D shape. And we take from the teacher model as well as the student model at different parts of the neural network. So these are like different blocks, and we try to match those matrices, these 2D matrices, and then try to decrease the distance between them using L2 laws. So that's how we we are seeing like what's the relationship between the input and output of a model, so that we can match this to the student model as well. So these relationships between the teacher model and the student model should match. So this is one kind of thing. So we have also two types of things in this case. So one type of relationship matching is between different samples. This was between different layers. So this was within different layers, and this one is between different samples. So, okay, what kind of relations does the teacher model has like sees between two different images? So if we have these 3 images of birds, so we will have to see like, okay, how does the teacher model see these images, and what kind of relationship is the teacher model making? So the teacher model, if the teacher model is clustering these images in the same close to each other, then the student model should also cluster these. So that is also where we are getting some sense. So these structures should match in both the teacher and the student model. So this is how they are matching, right? So this is relation information. So now we studied about looked at how what do we match in knowledge distillation. So we talked about matching logics, matching intermediate weights, the weights of actual the neural network. Then we talked about matching intermediate features, the activation maps in different layers. Then we talked about the attention maps. It is like intermediate feature maps, but attention maps is giving you information where the model is looking within an image, or paying more attention to while making its decision. Then we talked about this sparsity patterns, that, okay, where do the zeros exist mostly? And the pattern should match in both the models. And then we have on a much deeper level, okay, how do the models look at these different images, and how do they relate these different images to each other? So this sense should both prevail in the teacher model as well, like as it is prevailing in the teacher model, it should also prevail in the student model as well. So yes, so now we will talk about the loss functions that are used for matching in knowledge distillation. So the first and the most popular is the KL divergence. So this is the standard soft clause for matching the final output distribution. So this talks about the distributions in itself. So it measures the difference between the probabilities of the teacher model as well from the student model. And it is directly from statistical based. So to make the goal is to make the student's probability distribution like the teacher's one. Then the second one is the L2 loss. We can also match the probabilities using probability distribution using L2 loss as well. This is a really flexible one, and it is used to directly match the values of intermediate layers. So L2 loss, you can say it directly measures the distance between 2 points. So if we have 5 lodges from the teacher model and 5 outputs, like 5 lodges from the student model, then we can directly use L2 to measure the different distance. And we need to then minimize this distance while training the student model, right? So this can be used to like match intermediate features or feature maps, match the intermediate weights of the two models, match the in relational information that we discussed about a little while ago. And it can also be used as an alternative to Kullback-Leibler divergence for matching the final ledgers directly. So, and then finally, we have this cross-entropy loss. This has 2 key roles in the knowledge distillation process. One is the Hart loss. So I told you, like, when we are talking about classification tasks, so we use this cross-entropy loss generally, or whenever we talk about the classification tasks. So this is used for classification as well. So this is aside from knowledge distillation, but it is part of the overall knowledge distillation task when we are talking about knowledge distillation for classification tasks. And this is this is the part, the soft loss is the part that is specifically targeting the knowledge distillation part. So it can be used as the distillation loss where the teacher's soft probabilities are treated as labels for the students. So instead of providing labels to the student model from the data set, we provide labels from the teacher. So we will considering that, okay, the teacher's outputs are the labels in itself. So we will use the hard loss plus the soft loss in this case, and both will be using the this cross entropy loss in this sense. Now we'll talk about the different types of distillation training schemes that we have, and see how these teacher and student are trained together. So that is a little bit interesting thing to see. So this knowledge distillation is basically classified how the teacher and students are basically trained and updated during the process. So the first thing, first we'll talk about is the offline distillation. That is the distillation that we have been looking at until now, the normal one. Then we have the self-distillation, the online distillation, and we can combine these techniques as well. So first of all, this offline distillation, which we have been discussing about mostly. So teacher model are generally large in this case, and the student model is small, as we discussed. So we have some questions here. So what is the disadvantage of fixed and large teachers in this case? And does it have to be the case that we always have to fix the large teacher? Why not the teacher can benefit from the student as well in this case? So that is also an interesting point, and people thought about it. Okay, we can like also make this teacher dynamic in this case, and why not do that? So that's was an interesting question, and this led to this like online distillation as well as self distillation. So what we do in the self distillation, which is the second part that we are talking about, the second type of distillation here. So all the models, the teacher and student share the same architecture and they have the same size, right? So basically you are trying to train a single model, but you are training that single model in a knowledge distillation paradigm, right? You can say that your past self is basically sort of like a guiding thing for your current self. So this same thing is happening here. So if we have this initially we have this teacher one, this model, and this is the data. So this data is input to the single model, and this is trained on this data. Then in the second iteration, what we do is that, okay, we have this second model, but it is identical to the first one, and this is trained on the same data. And this previous model, the teacher that was previously trained, is now acting a teacher to this student one, to the S1, right? And this keeps going on. So much so that in each iteration, this like in this case, in the next iteration, this S1 would be the teacher to S2. And S2 would learn from this data as well as from S1. And this goes on. So SK minus 1 would be the teacher to SK. And SK would be training from the data as well as from SK minus 1. So at the end, you would see that the network accuracy of the last model, right? The last models in all of these iterations would have the highest accuracy. So this has been proven. And this paper was called Born Again. So a model is born again and again, and then it keeps learning and keeps getting better from the previous version. So that's how they named it. And interestingly, you can also use all of these models as an ensemble one. So you want to classify an image, for example, you put the image into all of the models and you get the shared results from there, and you average them out and you get the one final result. So you can say that, okay, if you could like copy yourself, your previous cells of previous days, and they all work together and provide something ingenious. So that's an example for this. So yeah, so now we talk about online distillation. So in this case, we have these multiple models, the teacher and the student models, or it could be like even more than these two. And they are trained simultaneously and updated in the same training process. So the student learns from the teacher learns from the student, and both of them also learn from the data. So this is like a mutual give and take process in this case. And turns out that both of them like you can benefit from this knowledge exchange. So we have this data and we have these two networks. So both of these networks output some logics and we have these predictions. So we need to like, okay, instead of like we having a single distillation loss for the student that we had previously. So for the student, this is the first student loss, and we have this cross entropy loss and the knowledge distillation loss. We also have a loss for the teacher now. And based on that, we are gonna update the teacher in this case as well after every iteration. And this would make both of them train and increase their capability. So this is also a way of doing that. So this is called basically deep mutual learning, and it can improve both the student net 2 and teacher net 1. So if we are looking at this table, you can see that we have two data sets, CEFR10 and CEFR100, and we have network types, net 1 and net 2. So you see that if we are training these models, net 1 and net 2 independently, they have these performances. But if we make them learn in a cooperative way, in a deep mutual learning paradigm, then the accuracy of the network here compared to network 1 here increases. Similarly, the net accuracy of the network 2 here also increases. And this TML is basically, this column is basically how much positive values, positive performance do we achieve in these two columns. And same for 100. So these are two data sets for classification tasks, right? And lastly, we can combine these multiple techniques. So by we mean that, okay, combining online and self-distillation. So by self-distillation, we mean that, okay, the previous model can be a teacher to the next model. And by online, so if we combine them, what would we like that? So it means like being your own teacher. So it combines self-distillation with feature-based knowledge distillation. So what happens here is that we have this single model, right? And what we do is that uh, starting from like these different points, we take these feature maps and we pass these feature maps to through these classification layers. Generally, we have this classification layer at the end of the model. Generally, we have this classification layer only at the end of the model, and we have these logics, right? But instead of only doing that, we also sample these feature maps from the intermediate layers of the neural network. And once we sample them, we have these, we pass them through FC layers, fully connected layers, and also through softmax. And then we match the logics of the output layer with these intermediate layers. So you can see that, okay, a model up until now is a smaller version of the model, complete model, right? So we have these smaller versions of the big model. And we want the big model to train its smaller versions. So this is basically the idea. So in other words, if we train our children, so it would be similar to that. So yeah, so this is also an interesting way of doing that. And yeah. Okay. So now we talk about, so let's re-summarize this. So we talked about offline distillation, that is the generic one, the first type of knowledge distillation. Then we talked about self-distillation, that the previous model becomes the teacher of the next model, and all the models are like have same architecture. Then we have online distillation, where both the teacher and student models contribute to each other and they learn from each other. And then we have the combined technique, in which basically the same model is training its smaller versions, and these smaller versions are part of the same bigger model. So this is an interesting paradigm. Now we talk about the different tasks that the knowledge distillation can be used for. So we have been talking about classification tasks. But other than that, we can like talk about object detection, in which we distill the classification as well as regression information. So classification, we know, okay, if you're talking about object detection, there I can see many people. So people can have these bounding boxes. So there are two things in this object detection. One is the classification. Okay, what object do we have in the image, and where it is located. So the information is provided, the answer to the where it is located is provided with the regression part. So this regression information could also be transferred using knowledge distillation. Then we have the semantic segmentation task. Semantic segmentation is a higher level classification task that is on the pixel level. So if we have an image, we want to label every pixel of that image, so that we have a fine-grained version of object classification in that image. So we can also do that. We distill features. We can also distill these pixel-wise loss, and often we can use this adversarial network training in that case as well. Then we have these generative adversarial networks. We can do that. So we compress the generative model in this case. And it can achieve like maximum extreme efficiency in this case using distillation, reconstruction, and adversarial losses. And this knowledge distillation thing is also used for making compact models, like this mobile BERT, which was created using this knowledge distillation. And you can like transfer attention maps and integer feature maps. So we have in transformers, we have like attention layers as well as the fully connected layers, and we can transfer the intermediate outputs to the smaller model as well, smaller transformer layer. Right. So thank you for listening on this knowledge distillation session. And if you have any questions, please go ahead. Thank you. I hope that it wasn't confusing or.
And it was. If you want to summarize, like, what is the difference between, what is the benefit of knowledge distillation? Because what if we train this model from scratch?
Mm-hmm.
We are only saving on training, or what other benefit we get from knowledge distillation?
Yeah, if we are like, for example, training from like generally it is like preferable to take a pre-trained model on any data set. And if you are using a pre-trained model or even from scratch, then even if you're doing it from scratch, so it is highly probable that it can learn from the teacher model, because it is imparting more information. So you have two sources of information. One is the data set. The second is the teacher model itself. So it is already highly probable that since you are taking from two sources, then the model would learn quicker compared to training from scratch only on the data itself, right? So it is something like similar to like, yeah. So it is similar to like, okay, if you didn't have a teacher and you have to like learn everything else, so it would take a longer time. But since you have teachers, so that's why we learn more quickly. Okay, so if no one has questions, then we can move towards a small demonstration here. Let me share the screen. Okay, yeah. I hope it's fairly visible. So yeah, now we are talking about this demo. I'm going to show you what we are doing here and what kind of technique we are using here for knowledge distillation. And it's like a simple example so that everyone can follow. So what we are doing here initially, this is a Python code for that, and you can access this Colab notebook from the repository that Obed shared. And if someone wants, they can message and Obed can share it in the messages. So let's talk about this code. So initially we are importing here some packages that is basically based on PyTorch and Torvision packages. And this is also like, we also use Matplotlib for like visualizing our results. Okay, so these are the hyperparameters of our training, our models, right? So we will be taking a batch size as 128. We will be training this for 10 epochs. And the learning rate would be like 0.001. 10 raised to power minus 3 is the learning rate. And these two hyperparameters are basically for knowledge distillation here. So we have this 10 temperature, T value that we had set. And the alpha, you can set anything. I just ran a fresh experiment here before this seminar started with a 0.7, and I wanted to check, okay, what kind of output do we get? So I did it with 0.7, but you can keep it 0.5 as well. It depends like how much weight do you want to give to the teacher model compared to the students' own learning, right? So basically this alpha determines that. In this experiment, we will be using the Cypher 10 dataset. That is an image dataset. We load it and like we set it up. And so this code is boilerplate code for that, for setting up the dataset for our experiment. Then we, as you can see, we are here, we are initializing a class for the student model here. And you can say that this is like really simple student model. We have only two layers in this model, two convolutional layers. And then after that, we just have two linear layers and we get the output. So a really simple model here. And for teacher model, we like get a really big model compared to our student model. This is like a 56 layered ResNet that was trained on Cepher 10 dataset. And it is loaded using the torch.hub.load function. Torch provides their own models. So we assign it as the teacher model. And we send this teacher model to the GPU as well as the student model as well. And the teacher model here is set to evaluation mode, meaning this is not going to take part in the training. Like it is not going to learn, but we are going to take its output for different images so that the student can learn. Okay. Then we are going to set up distillation loss. This function is for the distillation loss. So what we will be doing in this loss function is that we will send the student logits. By logits, I mean the outputs of the student model, the teacher logits, and as well as the labels. Labels are basically the actual image labels in Cypher 10 that we have for the specific batch that we are talking about. And T and alpha, of course, as well. The alpha is the weight that we want to provide to the teacher and the students, and T is the temperature value. So first we initialize our hard loss. By hard loss, we mean the cross entropy loss for, the actual classification task that we were performing for the student. So this would use the student logits as well as the labels from the dataset, from the batch that we got. And then we have the soft class. Here we are using the Kullback labeler divergence loss. And what we do here is that we take the softmax of the student logics, and basically we are doing the same thing here that we did, that I showed you the formula here, that was, for softening the logics and calculating the probability. So basically this is softmax function. We apply softmax function on the student logits and divide them by T. We do the same thing for the teacher logits and dividing it by T and pass them to the KL divergence. And we add this hard loss and soft loss here. This is the alpha. Basically, 1 minus alpha is the weight for the hard loss, and alpha is the weight for soft loss. Basically, this is basically the showing the knowledge from the teacher that would be imparted to the student. And this combined loss will be returned to the training loop, and based on that, we are going to update our student model. This script is for evaluation of the student model, how the student model is performing in each iteration. And this basically loop, this function is the training function. That is generally a PyTorch function that we use, right? That we write to train any model. So yeah. So once we run the experiment, and this we just run the experiment, we run the training, we use these optimizers and continuing. That is part of deep learning and kind of standard stuff. So once we run the training and track the progress, you can say that you can see here. First, what we did is that we tried to train the student model in a standard way, in an alone manner, right? No teacher, and we just want to train only the student model. So you can say that we have 10 epochs. We have been training the student model in 10 epochs. You can see that here, the accuracy of the student model is up to only 70 to 69%, right? But then we again perform the same experiment with knowledge distillation enabled. So now we are gonna teach the student model with the teacher as well as the data. So here you can see that the performance of our student model reaches up to 72.21%. So this is like around 2% more performance compared to the teacher model, right? So we have increased its performance. And one thing to note here is that, so this is the curve of the learning. So this blue one is without the teacher model, without knowledge distillation. And this orange one is with the knowledge distillation, right? That we had. So you can see that, okay, this makes a difference. And, we chose a very small model in this case. Like it was only 2 layers compared to whole 56 layers. And that 56 layer was also having these residual skip connections. It was the residual net. So if we select a better student model, like a brighter student model to select a good model, then it would even perform better in this case, right? So yeah, that was the demo. You can access this notebook and run your own experiments in that case. If you're interested with learning different hyperparameters, different epochs, selecting a different model, student model, selecting different distillation, knowledge distillation hyperparameters like the alpha and the temperature, it would be quite interesting for you to try out different things. So if you have any questions, yeah, so please. Anyone online, if anyone want to? Okay. So yes.
So I find it a bit difficult to have some intuition about this temperature. I mean, can you choose it to anything?
It depends. Generally, you can select it to 10 because it lowers the difference between the probabilities that the teacher outputs. So as I showed you, let me share the screen. So generally, it's like a 10 value, but you can experiment with different values as well. What is working for your current use case? So there is no, I haven't seen any mathematical theoretical justification for a specific value. But what you can do is that try out different values and what works in your case. In this case, initially, I also tried to try a few more values, and I saw, okay, the 10 value was working well. So this is something that comes from experience as well as a little bit, hyperparameter tuning, right? Okay, so we will have a short break of 15 minutes, and after that we will proceed towards knowledge neural architecture search, and yeah, so see you then. Thank you for listening.